welcome Johan Blom, and welcome with your presentation, an approach testing larger industrial systems. Welcome.
Thank you, Magnus. Thank you for inviting me. An approach testing larger industrial systems. Yes, it happens to be that I am one of the co-founder of Mobile Arts, and that is the reason why we had these problems and this kind of systems. I will show you a little bit more about later on. As I said, Mobile Arts. It's a small telecom company that develops server software for telecom operators. The software we developed there are placed in the kind of core network or close to the core network, and they are situated in big data centers out of reach for normal users. And talking with all the core network elements in the telecom network. And the implementations I'm talking about here is rather big and complicated. They are protocol based, as it often is in telecom networks and telecom applications. And what I'm going to talk about here is something that actually took place a number of years ago. And at that time, and maybe now as well, but I can only talk about what we had at this point. We were a group of very experienced developers, but we didn't have any testers. So whenever we implemented something, we had some problems and got feedback from the customer that sometimes it didn't work, and that could happen in the middle of the night. And that was okay as a startup, as an early startup. That was okay, but in the long run, we got like tired of that situation. So it was like we need to do something about this situation. We can't like have it like this and have like a wake up call in the middle of New Year's Eve or Christmas or something like that. So we were thinking about testing this then, of course. So I identified a number of core modules in the location server that I'm going to talk about here. We had other products as well, maybe actually more problematic than this one, but this was a nice first try, I was thinking. And we run executed dialyzer, which is a static type checker on it, and it looks pretty much okay, as you can expect if you have a number of experienced developers that tend to produce quite good code. And we also had a number of manual test suits that was running okay. Well, so as I said, everything wasn't okay, but the feeling was still that we were kind of confident that this was running quite well. Well, I wasn't really happy with that though, because I knew this couldn't be this good, and we had this proof as well that everything wasn't always okay. We had whenever there was something special happening, there was a high risk that something bad was happening because we hadn't tested exactly that use case or that combination of use cases. And the reason was simply because we hadn't tested everything. We had tested a few good test cases and the main functionality, but there was a lot of corner cases that was not covered by our tests. And we had this problem also that this product was, as I said, it was situated in the data center at the telecom operator, and we couldn't easily reach it. And it was also talking to a number of core network elements in the network, meaning that if we did something bad, it could be like we crashed the whole telecom operator network. And that happened, not for us, but we have heard like stories from others where this actually happened. or similar situation at least. And my approach to this was to use something known as model-based testing. So that was kind of setting the scope for the kind of testing I was looking for. That means that we wanted to capture the functional requirements. We wanted to create an executable model, because there is a workload in creating the model, but it's good if that could be like simulated or something, because that would actually simplify the creation of the model, and it could actually be used perhaps as a prototype as well. And then we use these executions of the model to generate traces. So this is a model that is like not implementation, but it's like a higher level of the implementation. That still should be like on this higher level. It should behave as the system. And this use of a formal model and generated test cases from that formal model, that is actually quite powerful, because from that model you can generate lots and lots of test cases for free, like once you have created a model. And this is nothing new. Already at that time, there's a number of tools existing. I list a few here. There might be more, and there might be even better ones today. I don't know. I haven't really checked lately. So I started to develop my own tool. Well, why should I use something existing when I can develop my own? And in the same time, making it more work better with the Erlang implementation we had of the system we had developed at Modelbased, I should say. That was developed in Erlang, so it was a complete Erlang system. And also, I had a number of years before that started to work on my PhD thesis, and we had some ideas on how to improve on these existing tools. So that's like the two main reasons for starting to do this work. Okay, so the rest of this talk, I'm gonna essentially hold to this picture of what Early March, the tool, is. And I'm gonna start in this upper corner here. From creating the model from some requirements. Okay, so as I said, the model represents an abstract view of the system. And here we are specifically interested in state machines, because that was protocols are built of. And that was you typically have in a telecom environment. And I thought that, well, I want something that is good in expressing something, what I want to express in a short and a consistent way. And there are a lot of, I think, good constructs in Erlang that makes Erlang actually a quite nice specification language. And then we had also this advantage in that we had the system built in Erlang. The developers understood Erlang, and it was also good if those specifying the system or thinking more higher level on the system could like have a common ground of so that they could understand, speaking the same language, so to speak. And then a third advantage was that we actually could use some Erlang tool infrastructure also on the model, like a parser, for example. And we wanted to create test cases that treated the system and the test as a black box. It's black box testing. And to do that, we introduced Erlang ERFSM as a specification language, which essentially is a subset of Erlang with a few minor extensions. So here we have a system, a state model. It should represent an extended state model where you have state variables and you have events. You have input events and you have output events, when you move and you start here in the green dot from whenever there is a SLEER event with 6 arguments, and then you output some ATI event, and then you move to another position here. So it's like that. You have input events and you have output events, and then during the execution here, you change a number of variables, a number of state variables, and eventually you will reach here in the end state, and then you are finished with the test case. So the Erlang ERFSM specification then, as I said, it's kind of similar to Erlang, but I and you should, if you are familiar with Erlang, you should be familiar with at least this box here. It's almost Erlang. The syntax is Erlang. Except, but I use now I should say immediately, if you are a purist Erlang functional programmer, that I cheated a little bit because I wanted to use this as a state machine. So I used some variables, for example. I declared them a little bit. I created these additional locations here for the state machine, and this is the idle location. And then we have this SLEER event. So I have created a convention here on how to specify events. So this is the idle state with a SLEER event, and then you have the number of the arguments to the SLEER event here. Might not be the most beautiful way of doing things, but that's the way I did. And then, as you see here, there's a guard here, checks the enforce PSI. That's an argument, and then this is another special thing. It's something that should represent a configuration parameter. And then we have the rest here. It should be kind of familiar. Okay, so that was a very short intro to the Erlang ERFSM language. And the second thing, so with this method now, we can generate a huge number of test cases. It's so many test cases that it becomes a problem. We need to select a set of them. And to do that, we have a number of tools or methods to do that. But the most important one is the observer. And again, of course, you have to create that observer, and it's based on some requirements. And then we also have to add that you may have complicated environments, so you can't really execute these. So in reality, there are limits on the test suite size that we can generate here. So then the question is how to find that optimal size of the optimal test suite. Well, I think one way to approach this is to introduce some flexibility, and that's where the observers comes in. And one observation is that there exists a lot of coverage criteria in the literature, and a coverage criteria could be like all locations or all edges or all definition use pairs that you can find during the executions. So all locations means that in the state the machine I showed you earlier, all those rings get covered by at least one test case. But although there are a lot of criteria, it's often unclear which one to use when, and you can define your own as well. So the motivation here was to use have a flexible enough method to we can just invent any coverage criteria. So the approach here was to use yet another specification language, Erlang OBS, and again use like a state machine for that observer. And this is what that could look like. As you can see, this is typically a lot smaller state machines, and the language you can express here is perhaps less related to Erlang, actually, although the syntax is still Erlang. I can still use the Erlang parser to parse that. What you have here is something called observer predicates. So here you start in the DU state, and then you look at some edge in your state machine, and you see that, oh, there's a variable defined here, and we are on some edge, of course. And that variable, that could be like any variable. So x here is actually a variable that is bound during execution to some variable that we find on this edge that is defined. And then you continue like that. You check with your observer predicates, and eventually you will reach the here, which is like the final state, which means that this observer accepts this test case or this execution as something that is like interesting or something that we are looking for. And then I should say also that you can't really define these observer predicates because they becomes crucial. You can't define them in Erlang ops, but you can define your own observer predicate in Erlang or in whatever language, and then you like link that into to this. So the idea is that you should be able to freely define any observer predicate with this tool, giving you a maximum flexibility. Okay, so then we have the two main components here, the model and the observer, and now we're going to create test suites. Well, as I said, observer is one way to limit the test cases or limit the practical implications we have when we have this huge number of test cases. Another one is symbolic execution. That means that we can handle sets of execution actually, because we treat the parameters symbolically. So if you think of this state machine now again, we take we take one edge here in the state machine, because we wanted to create a test case that goes from this start state to the end state. But in one state, we can see here, for example, this is just an example, that you have this a guard here, and you can execute this in two ways. You start here, and then this is true, this guard here, and then this guard is true, and then we end up here in next state. So that means that we move to another state. Or this is record is false, and we end up here, and you end up in this state instead. Two executions, and this is something we have to execute symbolically. That means that we end up with something like this. I'm sorry about the coloring here, it's kind of confusing, but you have to bear with that in the source code, I mean. So then we have like something to work on here for one edge, and then we do the same for every edge here until we reach the down state. And while we are doing that, we are also collecting the guards here that we get. As you can see, we got a slightly larger guard to this what's called edge clause here than we had in the previous picture, where in the model, I mean, the specification we started from. So then you end up with quite a large guard here when you have reached here and executed all the edges. Okay, that was execution, symbolic execution without observers. If we also add an observer into this, we can think of the observers as some kind of infinite set, or the observer as a process that spawns whenever needed. And we have infinitely many of these observers, so we can use them freely. And that will also result, of course, in a test case with symbolic parameters. So let me just elaborate a little bit on how this works then. So if you start here in the DU state, this is the observer execution, and this is the execution of the state machine. So we start here in the start state, both, and then you execute the first edge in your execution of the model. And then you can see, oh, well, here is a variable that is defined on this edge. Okay, that's okay. And we do have an edge. That's called E1 here. Then we record that and move on to the next edge. And we are still, this observer is still variable. Now it could happen here that we have another variable defined on this edge, and then we start another observer. So that would be like a concurrent execution of the observers. But okay, here we said, okay, for this observer to continue, we should not have a new definition of this variable MSID. And if that is the case, well, then we just continue. And it could be like, as you see, there's a loop here, so there could be a number of edges in the state machine that is updated. Until we finally reach some edge here in the state machine where we have this variable MSID used. And then we are like, then this observer accepts this test case as something interesting, something that we should keep, and keeps it. Okay, so now I was planning to show you a small demo here on what how this works in practice, the test case generation. Let's see if I can do that. Okay, I don't know if I should be able to see my screen here. So here I have defined a small observer. It looks for the target location. This is the observer predicate, is target lock. And if that accepts, we're going to end up here. And of course, we will always have a target location in an edge. We will start with a source location and a target location. So if I do that, I do like this. And then you can see here that I have a number of dead code. It's kind of ugly, but because that is a third way of limiting the number of test cases by adding projection properties. I shouldn't spend much more time on that, but it's like an invariant. Okay, we can see that it was quite quick. We were actually now searching the complete state space of this rather large model, approximately 3,500 lines. And it was quite quick, as you can see. Finding 5 test cases was needed for covering this observer here. And now we could test another one. Like that. And we can keep the names here. The lock and lock 2, they are just names, so they could be whatever. The interesting here is the edge. In practice, or in principle at least, you could execute multiple observers in parallel as well. Okay, so if I start that execution of that observer, I should get something else than 5 test cases. This is a little bit more complicated. And we ended up with 422 test cases here. Symbolic test cases, I should say. So, well, 422 with its all edges here. And then the def use, if I had executed the def use observer that you saw before here, that would be like 6,292 test cases. That takes a little bit longer. And all in all, it is possible to generate 82,000 test cases from this model. Symbolic test cases again. But I'm still working on the model, and I'm still creating symbolic test cases. So we are quite far from actually testing and using this. And the first thing you need to do with a symbolic test case is to fill in give the parameters in the symbolic test case some value. And if I do that, and if I just count all the possible ways I can instantiate these parameters I have in these 82,000 test cases, then I end up in, as you can see, there's a huge number of possible abstract test cases. That's still in the model. And the next step then, that would be to continue down further to the actually concrete test cases here. So I already said that. The next step, there will be to find mappings of the abstract test case into the concrete test cases. And that is something that is kind of outside here, but it means that you have to somehow map your abstract value into the concrete value. How you do that is something that you probably should think of when you create your model. I can imagine that you can use it for when you for testing as well. You can test different values here. So this means that you have how you choose this means that you can have a really lot of possible executions of this. And maybe you can use some random generation here as well. Okay, that's like the quick version of what this tool, model-based tool, was doing or is doing. And we actually use this at Mobile Arts for performing a larger case study. I don't have time now to reveal the details and the outcome of that, but I can tell you that I actually found more than 100 faults in this location server that was supposed to be like flawless or working fully without any problems with this tool, I should say. And that's about complete what I have to say. If you want to know more about this, you can read about this in this article here that explains more about the evaluation. You can also learn more about the whole approach, including the case study, the theory. I have defined formal semantics, etc. Both both languages and the mix or the combination of these languages that you end up with. And this is supposed to happen or end up in GitHub somehow. I have reserved a repo for it. There's not much there yet. It needs to be in some state in order for me to get it up there. But eventually, it will get there. I promise. Okay, that's what I had to say.
Thank you very much, Johan. You get an applause from me.
Oh, thank you.
Hopefully a digital applause from everyone. Thank you very much. I have some questions.
Oh.
I haven't received any questions right now from anyone.
Oh.
But if you have questions, please shoot in the chat and I will pop them up to Johan. I had one question I ask everyone that joins in. It's like, how come you ended up on working with Erlang?
Oh.
Was it a language of choice or was it more a coincidence?
It was a student project in 1991, I think.
So you were early on to functional programming.
I found out one of the Erlang conferences, there was a hand raise on who has used Erlang first, and I actually won a prize.
Oh, you did?
Yeah, I did.
What did you do as a student project?
It was a telecom kind of switch for Ericsson, of course. And I think they were kind of experimenting with Erlang and Erlang OTP. So we were like a trial users of that.
Cool. It's really cool. Then I have another question. It's like you said you work at Mobile Arts and then you started to, how do we test this geolocation server? Was it like you were interested in testing and that's why you ended up doing model-based testing? Or was it more, I'm lazy, I don't want to write all the test cases?
It was more like I'm lazy, I don't want to generate all the test cases. And we had this problem. And I also had, one motivation was that I had kind of a half-finished PhD and we had some ideas. And I thought I could just continue with what I was already started or just more or less. But I couldn't.
Okay. Another question is like, is this an open source tool or will you open source it?
Yeah, of course.
Yeah.
I intend to, but it's it's getting slow.
Oh, you have like lack of time like everyone else.
Lack of time, yes. And it's getting, there are some. I started refactoring because it ended up. I ended up doing like everything, Jenkins, whatever, in one tool, and that's a really bad idea.
Mm.
So I wanted to separate out these parts and make it more like components out of it, and that I started refactoring in that way. And then ending up, oh, that looks ugly, that part, and then I tried to drip other parts in there, and got like halfway with that before something else came in my way. So,
How long time did it take to develop the tool? Was it like?
oh, it was many years. I spent. I started. Oh, I don't even want to count. Actually,
Okay.
it's like 10 years or something.
Yeah. Okay.
I have put a lot of effort in this.
Yep. If someone wants to reach you and get the code, where can they find you? Facebook, LinkedIn, or you're on both?
I'm not on Facebook, but
No?
LinkedIn
Yeah.
should be possible to.
Yeah, you should search your name, Johan Blom,
Yeah.
PhD. I think they'll find you.
Yes.
Or you can find the link on Meetup, of course.
Yeah.
Or in the YouTube, below in the YouTube. We can put it up also
Yeah.
below the stream.
Mm.
Yes, thank you very much again, Johan.